city I. So that was part of the problem description. We were told that these were equal values. So if we look at this first circuit we drew, then we can follow it around this way. But we could also choose to go the opposite direction, so going backwards along all of the arrows. And this is obviously going to be exactly the same distance. If we're assuming that each of the individual distances is the same forward and backwards, then the total distance is the same forward and backwards. So those two circuits, the forward direction and the backwards direction, they would get counted twice in this way of counting. But we only want them to be counted once, and so we divide by 2. Okay, you just need to kind of think about it for a moment to see that that's going to eliminate all of the double counting that we want to eliminate, and it won't throw out any other circuits that we're still interested in.
-1.
The total number of circuits is n minus 1 factorial over 2. Okay, then the next part of the question, why isn't this working? There we go. So the next part of the question was to, the test it's always assumed that n is greater than 2. So if you had 2 cities exactly, I mean it's assumed that n is greater than 1 for sure. If you had 2 cities exactly, then you could have this tour, and that's the only one. That's the only option. And n minus 1 factorial over 2. Good point. What is, 1 factorial would give a half. Why? Does it work for 3? 1, 2, 3. And that should be the only one, right? Because if we went the other way, if we went this way, then that's just the opposite. Okay, so that gives 1. So that's correct when n is 3. N minus 1 factorial over 2 is 2 over 2, which is 1. Why doesn't it work for 2? Great question.
N is,
What are we not double counting?
n is equal or greater than 3.
So we've been to city 1 at the end, city 2 in the middle is only one choice. Right, okay, so because we never...
Initial value.
Right, okay. So in this case, we never did the double counting, did we? When we were working it out in this way, then we never did double count because it's obvious that going the other way round the loop is actually the same thing. We'd still be going to city 2 in either case. Yeah, so the formula doesn't work when there's only 2 cities, you're right. I hadn't noticed that before. That's really annoying. So the big O class is unaffected. Yeah, sure. Yeah, that is really annoying that the formula doesn't work for n equal to 2. Well spotted.
You're welcome.
The ceiling function will fix that. Yeah? Yeah, I'm not sure what the intuitive justification for using the ceiling function would be. What is this? It's really there can't be a cycle in the graph, which is what the TSP is about. Well, yeah, so you're right in saying that if there's only 2 cities, then there kind of is no problem, right? If there's only 2 cities, there's no question to ask about which is the quickest way of getting between them, because there's only one option anyway. Yeah, it is annoying that it doesn't work for 2 cities, but I suppose we just say we're not interested really in that case anyway, because there's no decision to be made about which way to go around these cities. I guess that's what you're saying, Lloyd. Yeah, so well noticed. How annoying. Okay, let's get a blank sheet. Right, in terms of the algorithm
Yo,
to
chill
find
out,
the
man.
distance, so our algorithm to find the distance is going to look something like this. So for each path in all paths, no, does not. For each possible path, we're going to say calculate the distance that's the distance of following this particular circuit round. And then let's have a minimum distance, which we will initialize to infinity or something big. It could be, I don't know. I'm just going to say infinity for the sake of the abstract version of the algorithm. And then we'll say if our value d here, the distance going around this particular circuit, is less than whatever we've currently got in the minimum distance, then we will update the minimum distance to be this. Okay, so we'll just go through all of the possible circuits. For each one, we calculate the distance, we compare it to whatever our best value is so far, and if it's better, then we keep it. If it's not better, we throw it away. So then the total running time is...
Bruda.
Well,
Charlie.
we have to do the number of iterations is equal to the size of all of the paths. So we know what that is. Let's work that out in the first part of the question. So the number of times we have to go through this loop is the number of different circuits we have in this set that we've called all paths. And then the cost of each iteration is equal to the cost of doing the calculated distance.
Chicha. With
This function. Plus some constants. So we've got one comparison here, and we've got an assignment here, possibly, but that's a constant number of operations. And the distance, what's it called? Calculate the distance.
multiply.
Calculate distance
I started with one church.
for a particular path. The cost of doing this is just adding up n numbers. So we've got our path, and each individual bit of that path between two cities has a distance associated with it, and we need to find the sum of all of those. So there's n of those individual distances, we have them up.
Multiply. Bank account, multiply.
Okay, so each addition is considered constant time, and we've got n of them. Okay, so then the total is, we go of n from here, because each time we do the iteration, it's we go of n, multiplied by the number of times we have to do the iteration, which is n minus 1 factorial.
Divided by
We
2.
lose the divide by 2 because we lose the constant factors when we're doing big O notation. And obviously n times n minus 1 factorial is just n factorial. Okay? So we had n minus 1 factorial, big O of n minus 1 factorial, total paths. For each path we do n things, so total.
Yuvraj, do you do combinatoric?
Do this kind of brute force algorithm. You can be a little bit clever at this point. Did anyone get a different answer from this out of interest? Silence, okay. So I think this is the answer that we were expecting. So n times by n minus 1 factorial is equal to n factorial. That's just by the definition of factorial. So n minus 1 factorial is equal to n minus 1 times n minus 2 times blah, 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 blah. And then multiply that by n and you get n times n minus 1 times whatever. And that's equal to n factorial. So that's just the definition of factorial. Yeah. Okay, so I won't show you the exact details of the little trick you can do, but I will try to give you an idea of it. So the idea is, each time you're coming through this iteration, you've got some circuit like this, and you want to calculate the distance. And each of these lines has distance associated with it. So there's n things to add up. Fine. We said we're expecting it to be bigger of n. How about if on the next iteration, instead of just picking another path arbitrarily, we specifically pick a path which is only a little bit different from this one. So maybe we could do this instead. So we switch these two cities over. Okay, so this part of the path is exactly the same as it was the previous time. We've switched two of the cities over, so we've changed some distances. And now we can use the calculation that we did in the previous iteration. And instead of adding up all n values again, we can take the previous distance. We'll take out.
Apparently we had a coursework due yesterday. I didn't even know of, man.
We'll add in these two that we do want, and then we've got our new distance. But that's only 4 extra calculations that we've done instead of.
I wonder if you can still submit today.
Calculations. And so if we order the paths in a particular way, so that we're very careful about only changing a little bit each time, then every time we do this iteration, we can remember the previous value. We can remember what we've changed about the path, and we can just do a smaller, a constant number of calculations each time to update distance so it's correct for the path that we're now considering. And so if we do that, then we get within the iteration, the cost per iteration becomes just constant, and then we end up with bigger of n minus 1 factorial, which is kind of nice. I think that's not particularly obvious, so if anyone did notice that, that's really good, well done. But if not, the bigger of n factorial is also a perfectly good answer, and that's kind of the obvious brute force algorithm. Okay, and we can do a little bit better on traveling salesman, but the algorithms become a little bit subtle. So for now, the brute force algorithm is fine. Okay. If you got the answer wrong, you get marks for engaging. I have no idea if you get credit purely for engagement. I assume the marks for the stretch exercises are for getting the answers right. But I don't know. But you get marks for doing the basic exercises as well. So you get 5% for each of them, right? So, right, what was the other question? So the stretch exercise was, it was writing another linear program. Lovely. Yes, so it was these two sons who were squabbling over the inheritance, we imagine. So we had a big long list of items, and I think in Teams there was some confusion about whether the items could be split up. So there were 2 dogs that had to stay together, and there were 3 diamonds which can be split up. So there were 11 different types of item listed, but these diamonds could be split up. So we ended up with 13 items in total, I think. Okay, and then each item had value associated with it. So we ended up with, so we've got 13 items and 13 values. So we're going to have decision variables. We're going to have values. So for item 1, we'll let the decision variable be x1 and the value be b1, and so on. So for item I, we've got xi and vi. Now, xi is equal to 1 when brother 1 gets item I. And we're assuming that all of the items have to be shared out, so it's equal to 0, means that brother 1 doesn't get it, so brother 2 does. And then we wanted to minimize the difference between the values that they get. So brother 1's total value is the sum of vi times xi, because xi is 1 when he gets the item, and then he gets the total value, and if it's 0, he doesn't get any value from that thing. Brother 2's value is the sum of vi times 1 minus xi, because then when xi is 0, this whole expression becomes 1, and he gets that value from vi. So then we are minimizing the difference between these. And kind of the trick with this problem was to say that we will assume that brother 1 gets more. So that allows us to get rid of these absolute values, and we just add in a constraint saying that that's what we've decided, basically. Because we don't care which way round the brothers are. So once we've done that, then we want to minimize z equal to, get rid of the absolute value, so sum of vixi minus this, vi1 minus xi, and then we can just rearrange that, and so you end up with z equal to twice the sum of dixi minus the sum of vi. Okay, and then we're subject to the assumption that brother 1 got more. So that was the assumption that this is greater than this. Okay, so then you can rearrange that, which is what you end up with. Sum of vixi is greater than a half. Sum of vi. Okay, so we have, this is our objective function up here, this is our constraint. And the other thing, we also need that the xi's are in 0 and 1, obviously. And then the other thing we can do to simplify it is we actually don't need to keep this value here because that is a constant. So it depends on why you're doing why you're making this formulation. If you get rid of this constant value, you'll still get the same answer in terms of who gets which things. But then when you plug it back into the z, this won't give the same result. So it won't tell you the difference. So if you want to know the difference in the end, then keep the constant value. If you're only interested in finding the correct choices for the xi, then you don't need to keep the constant value in the objective function. Okay? So in the end, again, this quite complicated setup ends up making quite a simple problem, linear programming problem. Okay? So hopefully you've got somewhere with those, and I think the answers will be circulated as well in the next couple of days. We'll try and get the marks back to you as well this week. Okay, we'll see you next week, and I expect we'll have even more simplex examples to go through.
Yeah, make sure you call me. I wanna do my thing. Hi. Bro, you're joking, man. I just missed all the calls wrong, man. Fuck. Yo, listen, I'm gonna call you in a bit, yeah? I'm gonna call you later in a bit. This is my first tutorial after 3 weeks. It's crazy. I missed the courseworks. Shit is crazy, man. Apparently, you had a solution for this module yesterday. You didn't even tell me, Arif. What's wrong with you? Anyway, man, I'll call you later, yeah? Take care.